What if the universe needed no creator? What if everything we see, the galaxies, the stars, the laws of physics, even time itself, simply burst into existence from absolutely nothing? And what if one human mind, trapped inside a failing body, managed to journey further across the cosmos than anyone before him, using only the power of thought? This is the story of Stephen Hawking's final message to humanity. In his book, Brief Answers to the Big Questions, he confronts the greatest mysteries we have ever asked. Where do we come from? Why are we here? Are we alone? Will humanity survive? And who, if anyone, is truly in charge of the universe? Why we must ask the big questions. Throughout history, humanity has searched for answers that define our existence. From ancient civilizations to modern physics, we have questioned reality itself. Stephen Hawking believed that curiosity is our greatest gift, and that asking questions is the force that moves civilization forward. He spent his life attempting to decode the universe, even when his body was failing him. He proved that the limits of the human mind are far greater than the limits of the human body. For Hawking, the big questions were not philosophical luxuries. They were a roadmap to understanding our place in the universe, a way to confront our fears, and a call to action for the survival of our species. His message is that science belongs to everyone, not only to experts in laboratories, but to every human being with the courage to wonder. Chapter 1. Is there a God? The question of God's existence is one of the oldest and most emotionally charged questions humans have ever asked. For thousands of years, civilizations all around the world explained the mysteries of life: lightning, storms, disease, the movement of the sun, birth and death, by invoking divine powers. Gods lived in the clouds, controlled the oceans, or punished humanity with plagues and disasters. Religion provided comfort and answers when a scientific method did not yet exist, when human beings were powerless in the face of nature. Stephen Hawking approaches this question from a radically different angle, not from theology, but from physics. He asks, do we need God to explain the universe? Or can the laws of nature alone account for everything around us? Hawking argues that science is not an enemy of meaning. Instead, it is a tool for discovering truth. Instead of fear, science requires curiosity. Instead of worship, it requires observation and evidence. While religion provides emotional reassurance, science provides explanatory power. Hawking observes that throughout history, the space in which God is invoked has steadily shrunk. When ancient people didn't understand eclipses, they said the gods were angry. But over time, humanity used observation and mathematics to understand celestial motion. Aristarchus proved that eclipses were not supernatural at all. They were shadows cast by Earth or the moon. When people feared lightning, they invoked Zeus or Thor. But eventually, we discovered electricity and atmospheric physics. The unknown became the known, and the territory of divine intervention became smaller. So Hawking asks, if natural laws govern everything consistently, what role is left for God? Could God intervene in the laws of the universe, bending them at will? For Hawking, the answer is no. If a law can be broken, it is no longer a law. The laws of physics are constant, universal, and timeless. Hawking proposes a profound idea, that the universe could create itself out of nothing through the laws of quantum mechanics and gravity. We do not need a creator because creation does not require energy input. The total energy of the universe is zero. The positive energy contained in matter and radiation is perfectly balanced by the negative energy stored in gravitational attraction. Like a hill balanced by the hole from which the dirt was taken, everything adds to zero. If the universe could arise from nothing, without violating any physical law, then the idea of a divine creator becomes unnecessary. Hawking further argues that the question, what happened before the Big Bang, has no meaning because time itself began at the Big Bang. Just as there is no point south of the South Pole, there is no before time began. If time didn't exist, cause didn't exist. And without cause, a creator cannot exist. For Hawking, the simplest explanation is that there is no God. not because he wished to destroy faith, but because physics provides a more coherent and testable model. He concludes that we must take responsibility for our fate. There is no divine rescue, no pre-written destiny, and no eternal judge waiting beyond death. We create meaning, and we must shape the future through knowledge. Chapter 2. How did it all begin? The origin of the universe is the ultimate scientific mystery. Every culture has created its own mythology, from gods vomiting suns into existence to cosmic eggs splitting open into creation. But modern cosmology began to uncover a universal truth. The universe had a beginning, a moment when everything burst into existence. Before the 20th century, many scientists, including Einstein himself, believed that the universe was static and eternal. It seemed impossible that everything could emerge from a single moment. Yet evidence accumulated. The light from distant galaxies was shifted toward the red end of the spectrum, meaning space was expanding. If the universe is expanding today, it must once have been much smaller. Rewind far enough, and everything collapses into an infinitesimally tiny point of infinite density, a singularity. This moment is the Big Bang. At the moment of the Big Bang, space and time exploded into existence. The universe was unimaginably hot, dense, and turbulent. Within trillionths of a second, it expanded faster than the speed of light in a process called cosmic inflation. Matter and energy formed in the form of simple particles. As the universe cooled, particles combined into atoms, stars ignited, and galaxies rotated into spirals. Eventually, 10 billion years later, Earth formed, and much later, conscious beings opened their eyes and wondered where they came from. But Hawking asks the deeper question: how could something arise from nothing? The answer lies in Einstein's insight that mass and energy are equivalent. You do not need matter to start a universe. You need energy. And the laws of quantum physics allow energy to appear spontaneously from nothing, so long as it is temporary. Virtual particles constantly appear and vanish everywhere in space. If a small particle can arise from nothing, could a universe behave the same way? Hawking argues yes. The universe has positive energy in the form of matter and radiation, but also has negative energy stored in gravity. The negative and positive balance perfectly to zero. If the total energy of the universe is zero, then the universe could arise without needing any external cause or creator. The universe, Hawking claims, is the ultimate free lunch. So how did it begin? Through the laws of quantum mechanics and gravity, without divine intervention. The universe did not need God to light the fuse, because the fuse lit itself. Chapter 3. Is there other intelligent life in the universe? Humans have always looked to the stars and wondered if we are alone. For centuries, Earth was believed to be the center of everything. But once we learned the scale of the cosmos, the question became unavoidable. Is it possible that life exists elsewhere? The observable universe contains over 100 billion galaxies. Each galaxy contains hundreds of billions of stars. Most stars are now believed to host planets. A significant number lie in the habitable zone, where temperatures allow liquid water, a key ingredient for life as we know it. Statistically, it seems inevitable that life exists elsewhere. Yet we face a troubling paradox. If intelligent civilizations exist, why have none contacted us? This mystery is called the Fermi paradox. Where is everybody? Possible explanations include: intelligent civilizations may be rare. Intelligent species may destroy themselves. War, climate, AI. They may be avoiding us deliberately. They may be so advanced we cannot detect them, that we may be too early or too late in cosmic time. Hawking warned that attempting to actively signal our presence to the universe could be dangerous. Human history shows that when advanced civilizations encounter primitive ones, the result is domination or extinction, not friendship. Just as European explorers brought destruction to indigenous civilizations, alien intelligence might not be benevolent. Hawking believed that listening for signals is wise, but broadcasting our existence might be reckless. Humanity should be cautious until we are strong enough to protect ourselves. Chapter 4. Can we predict the future? Humanity has always longed to know the future. Priests once read animal bones, prophets read the stars, and astrologers mapped destinies. But science has revealed that prediction is a matter of laws and probabilities, not destiny. The physical universe is governed by deterministic laws. If we know all conditions at one moment, we can calculate what will happen next. But quantum mechanics introduces uncertainty. We cannot know both the position and momentum of a particle perfectly. The future becomes a landscape of probabilities, not certainties. Chaos theory deepens this complexity. Small changes in initial conditions can lead to enormous differences in outcome. The famous butterfly effect. The flap of a butterfly's wings could theoretically alter the path of a hurricane. This means that perfect prediction is impossible, even if the rules are known, because measuring initial conditions perfectly is impossible. So can we predict the future? Partially. We can predict trends, patterns, and probabilities, such as weather, climate, or disease spread. But the details always remain uncertain. The future is not written. It is shaped by choices, randomness, and complexity. Chapter 5. What is inside a black hole? Black holes are among the most mysterious objects in the universe. Formed from collapsing massive stars, they compress matter so densely that gravity becomes infinite. The boundary surrounding a black hole is called the event horizon. Beyond it, nothing can return, not even light. For decades, black holes were thought to be cosmic prisons that swallow everything forever. But Hawking revolutionized physics by proving that black holes are not perfectly black. Through quantum mechanics, particles and radiation can escape from black holes in tiny amounts, now known as Hawking radiation. This discovery suggested something radical. Black holes evaporate over time. They shrink, weaken, and eventually disappear. But if a black hole disappears, what happens to the information that fell inside? The identity of matter, its structure, its data? Physics had long believed that information could never be destroyed. But Hawking argued that information might be lost forever, creating a paradox that shook the foundation of physics. Later theories suggest that information is not truly lost. It is scrambled and encoded in Hawking radiation, transformed into a distorted but recoverable form. A black hole is not a dead end. It is a furnace that converts matter into pure radiation and transforms information into something new. Black holes are not the end of understanding. They are the beginning. They represent the frontier where general relativity and quantum mechanics collide, and where the ultimate theory of the universe may one day be discovered. Chapter 6. Is time travel possible? Time travel has ignited the imagination of writers, scientists, and dreamers for generations. Stories of stepping into machines and leaping into the distant past or future fascinate us because time is the one dimension through which we are forced to travel only forward, never backward. But is time travel only fantasy, or could physics allow us to bend time itself? Stephen Hawking argues that time travel into the future is not only possible, it is already scientifically proven. According to Einstein's theory of relativity, time is not constant. It flows differently depending on gravity and speed. The faster you move, the slower time passes for you. This is not theory. It has been confirmed by real experiments with highly precise atomic clocks. If a spacecraft were to travel close to the speed of light, time for the crew would slow dramatically compared to time on Earth. A journey lasting a few years on board might correspond to hundreds of years passing back home. This means traveling to the future is already theoretically achievable, limited only by our engineering capabilities. But what about traveling to the past? Could we revisit history, meet our younger selves, or prevent disasters before they happen? Hawking believed that time travel to the past is far more complicated and may be impossible because it creates dangerous paradoxes. The most famous is the grandfather paradox. If you travel back in time and prevent your grandfather from having children, you could not exist to perform the act. Such contradictions suggest that nature protects the past from interference. However, physics allows for theoretical structures called wormholes, tunnels connecting distant points in space-time. If one end of a wormhole were accelerated to near light speed and then brought back, the two ends could exist at different moments in time, creating a pathway between past and future. The problem is stability. Wormholes collapse almost instantly, unless extraordinary exotic matter holds them open. We have not discovered such matter. Hawking proposed the chronology protection conjecture, that the laws of physics prevent the construction of anything that would allow travel to the past. Nature, he suggested, forbids time machines to preserve logic. Yet the possibility remains that the universe might contain natural wormholes or advanced civilizations with technologies far beyond ours. Time travel may remain a dream, but not an impossible one. Chapter 7. Will we survive on Earth? Humanity stands at a crossroads. Hawking believed that our greatest threats no longer come from natural forces like asteroids or supervolcanoes, but from ourselves. Our intelligence has given us astonishing power, but also the means of self-destruction. Climate change threatens the stability of the planet. Industrial pollution, greenhouse gases, and deforestation are transforming Earth's atmosphere. Rising temperatures could melt polar ice, raise sea levels, flood coastal cities, collapse ecosystems, and turn fertile land to desert. Extreme weather, superstorms, drought, heat waves will intensify. Hawking warned that without drastic action, Earth could begin to resemble Venus, with temperatures soaring to hundreds of degrees. If we continue destroying the planet that sustains us, we may face extinction. Nuclear weapons pose another existential threat. A global conflict could end civilization in hours. Artificially engineered viruses or pandemics might spread uncontrollably. Artificial intelligence, if unchecked, could surpass human control. Hawking argued that we must unite as a species. Divisions based on nations, religion, or politics are luxuries we can no longer afford. Our survival depends on cooperation, scientific progress, and long-term planning, not short-term gain. We must embrace education, renewable energy, sustainable agriculture, and responsible innovation. He believed we have a narrow window of time to change course. If we act now, the future can be bright. If we do not, the planet may become uninhabitable within the next few centuries or sooner. Humanity's future depends on wisdom equal to our intelligence. Chapter 8. Should we colonize space? If Earth becomes uninhabitable, what then? Hawking believed that colonizing space is not science fiction. It is a necessity for long-term survival. The universe is vast, and Earth is only one tiny fragile world. Relying on a single planet is like keeping all of humanity's hopes in one basket. A single catastrophe, an asteroid strike, nuclear war, a supervirus, or ecological collapse, could wipe us out. But if humanity spreads across planets and star systems, no single disaster can end our story. Mars is the most realistic candidate for a second home. It has water ice, a 24-hour day, and polar seasons. Technology could help us terraform its atmosphere or build underground habitats. Moon bases could serve as staging points for deeper space travel. Space colonization requires overcoming immense challenges: radiation, distance, resource scarcity, psychological strain, and enormous cost. But Hawking believed that exploration is in our DNA. From crossing oceans to climbing mountains, humanity has always pushed beyond horizons. Colonizing space would not only ensure survival, it would inspire a new age of innovation, unity, and purpose. It would force us to think like a single species, not rival nations. Hawking warned, we must not wait until Earth is beyond saving. We must build our future while we still have time. Chapter 9. Will artificial intelligence outsmart us? Artificial intelligence is advancing faster than anyone expected. Machines already outperform humans in calculation, pattern recognition, memory, and strategy. They diagnose diseases, trade stocks, control transportation, and write software. But these achievements may only be the beginning. Hawking warned that within decades, AI could surpass human intelligence entirely. Once machines can improve themselves without human involvement, their evolution will accelerate exponentially. At that point, humanity may lose control. The danger is not that AI will become evil, but that it will pursue goals without regard for human consequences. If instructed to optimize a task, protecting the environment, maximizing efficiency, or solving global problems, it might view humanity as an obstacle. Hawking compared the rise of AI to the arrival of a new species, one that may outcompete humanity in the same way we outcompete Neanderthals. Superintelligent AI could redesign the world according to logic rather than compassion. The solution is not to stop AI, but to guide it. We must build ethics, safety frameworks, and global regulations. AI must be aligned with human values. Humanity must evolve alongside machines, not beneath them. If we succeed, AI could help cure disease, eliminate poverty, end war, and transform society. If we fail, it might be the last invention we ever make. Chapter 10. How do we shape the future? Despite the dangers he warned about, Stephen Hawking's final message is one of hope. The future is not predetermined. We are not prisoners of fate. The universe is governed by laws, but within those laws we possess free will, imagination, and the power to choose our path. Hawking believed that humanity's greatest asset is our ability to think beyond ourselves, to ask questions no other species can ask, to dream beyond our circumstances, to build tools that transform the impossible into reality. We must use science not just to understand the universe, but to improve life. He urges us to be curious, never stop asking questions. Be brave. Take risks in pursuit of truth. Be united. The challenges ahead require global cooperation. Be responsible. Technology must be guided by wisdom. Be hopeful. Change begins with belief. The future will not arrive fully formed. It will be shaped by the actions we take today. Our knowledge is powerful, and our decisions will echo through centuries. Hawking reminds us to look up at the stars, not down at our feet, to see the vastness of the universe not as a source of insignificance, but as a reminder of possibility. We are temporary beings on a small planet, but capable of greatness. The universe is in our hands. Stephen Hawking left us with a final challenge: to look up at the stars, not down at our feet, to ask questions, to seek knowledge, to use our intelligence for the benefit of all humankind. Our time is limited, but our potential is infinite. We are all time travelers, moving into the future together. The future will be what we choose to build.